Hello students, welcome back to the classroom point. So in our today's topic, it is equilibrium. So in equilibrium, we should learn certain important terms and definitions to understand the main concepts of the equilibrium. So let us try to see for which type of the process the equilibrium concept is applicable. So let us try to see here. The reactions are basically classified into the two types. They are irreversible reactions and reversible reactions. Irreversible reactions and reversible reactions. Let us see what are the irreversible reactions. So if you take any particular reaction, reactants converts into the product. So the conversion of reactants into products is called the forward reaction. In case of irreversible reactions, only reactants always convert into the products. Products cannot be converted back into the reactants. Such type of reactions are called the irreversible reactions. So let us see which are the irreversible reactions. Examples. Usually, acid-base neutralization reactions are irreversible in nature. For example, if you take NaOH, react with hydrogen chloride, produces NaCl plus H2O. So here NaCl don't react with the water to reproduce the NaOH and HCl. So this is an example of the irreversible reaction. Similarly, precipitation reactions. So precipitation reaction means precipitate will be formed. Example, AgNO3 silver nitrate on reaction with NaCl produces silver chloride white precipitate along with NaNO3. And other category is nuclear reactions. Nuclear explosions are also irreversible in nature. Next one is some decomposition reactions also. Decomposition reactions. Example, potassium chlorate 2KClO3. If it is decomposed, it gives potassium chloride plus oxygen. So these are all irreversible reactions. In case of irreversible reactions, concept of equilibrium is not applicable. Reason is equilibrium in the sense balance. If you take the measuring one, so in that measuring balance, if you try to keep both sides equal amounts of the substances, then automatically after a certain time, you will get the balancing. So balancing achieved in a particular process is called the equilibrium. But in case of the irreversible reactions, since only one side process is happening, so for all this type of the process, equilibrium concept cannot be applied. Now let us see for which type of reactions a concept of equilibrium is applied. That is reversible reactions. So what are the reversible reactions? Reversible reactions means in these processes, reactants converts into the products. Products also can be converted back into the reactants. Since both sides processes are possible, these are called the reversible reactions, and these reversible reactions are indicated by using the half-headed arrow mark pointing in the opposite direction. So in this type of reversible reactions, every time there is a reactant and product, both reactant and product coexist in the reaction vessel. So for such type of the process, equilibrium stage can be attained. Now let us see here, the conversion of reactant into the product is called the forward process, or it is also known as the forward reaction. And the conversion of the product into the reactant is called the reverse reaction or backward reaction. And here we have to introduce one more concept, that is rate. The rate of conversion means in a given time how many number of reactant molecules are converting into the products is called as its rate. Example, if you take 100 reactant molecules, out of 100 reactant molecules, every 1 second 10 reactant molecules are converted into the product, then the rate of forward reaction is called the 10 molecules per second. At the same time, product also has the ability to convert back into the reactant. Its speed, the speed of conversion of the product molecules into the reactant molecules is called the rate of backward reaction. So for forward process, the rate is called the rate of forward reaction, denoted by the symbol RF, and for the backward process, it is denoted by the symbol RB. At equilibrium always, at equilibrium, rate of forward reaction is always equals to the rate of backward reaction. Now let us try to see how to achieve this rate of forward reaction is equals to rate of backward reaction in a particular equilibrium process. And this is based on the extent of reactions that are going to finish in the reversible processes. The reversible reactions are classified into 3 categories. There we will apply the concept of the rate of forward reaction equals to rate of backward reaction. So these are classified into 3 categories. The reactions in which reactants almost convert into products. That means this type of reactions we can show like this. Reactants almost convert into the products, but products don't want to convert with the same speed towards the reactants. So reactants have the more readiness to convert into the products, but products are not that much ready to convert back into the reactants. So in this type of reactions, more reactants are converted into the products. So at the end of the reaction, there shall be more concentration of the products rather than the reactants, because reactants convert into the products. The equilibrium stage is obtained at the end of the reaction, almost at the last stage of the reactions, and most of the cases this type of reactions cannot be recognized whether the reaction achieved equilibrium or not, because one of the concentration of the compounds is dominating, that is products are dominating than the reactants. So here I can write down that concentration of the reactants is less than the concentration of the products even at the equilibrium stage. So we shall take an example here. Imagine at time t equals to 0 seconds. That means reaction not yet begin. I am starting the reaction with only reactant molecules. Remember, equilibrium reactions or reversible reactions can be attained or can be achieved by taking either reactants or products. Why? Because they are completely reversible. If you take reactants, they convert into the products. If you take products, they also reproduce the reactant molecules. Again, they come to the balancing stage. So in this case, imagine I am taking the 10 moles of the 10 molar concentration of the reactant molecule, and initially 0 molar concentration of the products are there. After 10 seconds of the time, out of these 10 moles, imagine 4 moles converted. So remaining reactant molecules are concentration is 6 moles. Here I can write down the 4 molarity. I am taking directly in terms of the moles per liter. Hence I am writing the molarity. After 20 seconds, out of 6 moles, imagine 4 more moles are converted. So remaining 2 molarity of the concentration of reactants are there. And here now 8 molarity of the concentration of the products are there. Next, after 30 seconds, again you observe that 2 molarity and 8 molarity is still present. After 40 seconds, again 2 molarity and 8 molarity was observed. Even after infinite time, you observe that 2 molarity and 8 molarity is obtained. That means in this type of reaction, if you observe the data given here, reactant molecules more converted to the products. That's why more amount of the product is produced, but products are not willing to convert that same speed into the reactant molecules. That's why after 10 seconds, when the 20th second, after 20th second onwards, so they reached sufficient concentration of the reactant and products. From here onwards, there is no change in the concentration of the both reactant molecules and product molecules. So we can say that the reaction achieved equilibrium stage. So at any stage of the reversible reaction, wherever there is no change in the concentration of the reactants and products, that stage is called as the state of equilibrium. So in this state, here equilibrium is obtained. If you observe the starting cases, first two cases, rate of forward reaction is dominating the rate of backward reaction. But from here onwards, rate of forward reaction is equals to rate of backward reaction. Rate means, see the speed at which reactants are converting into the products. With the same speed, products also start converting back into the reactants only from here onwards. Starting, there is a difference in the rates, but now onwards, they will have the sufficient rates. That means, the rate of conversion of the products to the reactants becomes equal only when this much concentration of products and this much concentration of reactants are present in the reaction vessel. Otherwise, for this type of reactions, equilibrium cannot be achieved. Now let us see the another category. So reactions in which reactants hardly convert into products. Now, reactants don't want to convert into the products, so that we can show with a smaller arrow mark. Products are there, but products want to convert back into the reactant molecules. That means, for this type of reactions, equilibrium achieved at the starting of the reaction only. For this type of reactions, equilibrium achieved at the end of the reaction. So for this type of reaction, since reactants are not converting into the products, whatever the little amount of the product is produced, that is also ready to convert back into the reactants. So obviously we can easily guess that in this particular reaction, at the equilibrium, concentration of reactants dominates the concentration of the products. Again, as usual, let us take with 0 seconds. Initially 100 molecules are there. Imagine 100 molecules of reactants. Here 0 molecules of products are there. After 10 seconds, out of 100, 40 molecules converted. Since let us take only 10 molecules are converted, so that 90 molecules of reactants and 10 molecules of products are present in the second of time. Next 20 seconds, same 90 molecules of reactant and 10 molecules of products are there. Even after 30 seconds and after infinite time, same concentrations they do maintain. That means for this type of reactions, see, from here onwards, there is no change in the concentration of reactants and products. See, you should remember one point, that at equilibrium, the concentration of the reactants and products not necessary to be equal. Only rates must be equal. The concentration of the reactants and products may or may not be equal. So that is the reason in this case, even at equilibrium stage, rates are equal, but concentrations are not equal. Now, in this case also, from here onwards, at this stage, rate of forward reaction is equals to rate of backward reaction. So, from here onwards, rates are equal, but concentration of the reactants are dominating than the concentration of the products. Now, let us see the third category. Reactions in which reactants sufficiently converts into products. Example, let us take some P is converting into the Q. So when almost equal concentration or nearly equal concentrations are present, so for such type of the equilibrium reactions, we use this type of the arrow mark symbol. That means both, not only rates are equal, even concentrations also to some extent equal. But nowadays people are not using this one. They are directly using only this type of the symbols to represent the equilibrium concentrations. So imagine 10 molecules are there here at t equals to 0 seconds. Here 0 molecules are there. After 10 seconds, imagine 4 molecules converted. Here 6 molecules are there. So here 4 molecules are there. After 15 seconds, imagine one more molecule converted. That means here 5 molecules are present. Here also 5 molecules are present. After 20 seconds, same 5 molecules, 5 molecules. After infinite seconds, same 5 molecules, same 5 molecules are there. That means in this particular reaction, equilibrium is achieved at this particular stage, from where the rate of forward reactions becomes equals to rate of backward reaction, and the concentration of reactants also, here we can see that equal in there. Concentration of P is equals to concentration of the Q. In this case they are equal. Most of the cases they may or may not be equal. Some cases here also equilibrium achieved, so that concentration of the P could be more than the concentration of the Q. So this type of the concept is applicable. But here lot of difference is there. Here little difference in the concentration, here more difference in the concentration is observed. Now let us see equilibrium in physical process. So that is called as physical equilibrium. Usually physical equilibrium can successfully applied to the phase transformations. So for phase transformations, it is easy to apply as well as easy to observe the equilibrium process also. So what are the phase transformations equilibriums here? So let us take example. Solid liquid equilibrium, liquid gas equilibrium, solid and gas equilibrium process. So let us pick up everyone and we will have the comprehensive discussion about these equilibrium processes. So the first one is solid and liquid equilibrium. So let us take a thermos flask. So thermos flask means you know that it is completely having the it doesn't look like a flask, but imagine this is a thermally insulated container. So the walls are made up of the thermally insulated material. So that these walls do not allow any heat exchanges with the surroundings. It can be called as the isolated system now. In this, you take 1 kg of the water or 1 liter of the water. And drop the 1 kg of the ice. You know, ice floats over the water. And try to keep the temperature and pressures. Pressure is equals to 1 atmosphere or equals to 1.013 bar. And temperature is equals to 273 kelvins. That means it is 0 degrees centigrade. So now ice and water do coexist at this atmospheric pressure and 273 kelvins. Remember that 273 kelvins temperature is the melting point of the ice, and the same temperature is the freezing point of the water. So after a certain time, what we can guess? Whether the mass of the ice increases or decreases, or the volume of the water rises up or decreases. That means, see, both are in equilibrium state. That means, once this temperature is reached, ice starts melting into the water. At the same time, water molecule starts freezing into the ice. So that activity takes place only at the junction, means wherever this interface, wherever the ice surface meets the water molecules, there only melting process as well as the freezing process both together takes place. But here, after certain time also, you can observe that there is no change in the mass of the ice. At the same time, there is no change in the volume or mass of the water. That means rate of melting becomes equals to rate of freezing. How could this happen? Why? Because we did not allow change of the temperature as well as the pressure here. Automatically there is an equilibrium state attained between this ice as well as the water. What is the rate of melting and rate of freezing? Means if 10 molecules of the ice melts into the water in a second of the time, at the same second of the time 10 water molecules freezes into the ice. So that is the reason why, since both process occurs continuously, then there is no change in the mass of the ice as well as the mass of the water. And here, this system, can we say that the process completely stopped? That means melting of the ice and freezing of the water? No. Why? Because the process is not stopped, but the process takes place with equal speed. So such type of the equilibriums are called as the dynamic equilibriums. So in our concept, whatever we are discussing, they are all dynamic equilibriums. That means even after reaching the equilibrium stage, there is no stoppage of the reactants into products and products into reactants. They continuously starts converting into reactants into products and products into reactants, but with equal speed. That's why the process continuously takes place, but there is no change in the concentration of the reactants and products. That's why such type of equilibriums are called as the dynamic equilibriums. Static equilibrium means once after reaching the equilibrium, process do not takes place. That means reactants don't convert into products, products don't convert into reactants. Such type of the equilibrium is called as the static equilibrium. We are not going to discuss the static equilibrium. We are discussing only about the dynamic equilibriums. Next, second one is liquid gas equilibrium. So to observe this type of equilibrium, let us take a beaker. Which is connected to the manometer that is useful in measuring of the pressure. So this is completely empty beaker. In this empty beaker, starting we will take, in this beaker we shall take the calcium chloride, or you can take the phosphorus pentoxide. These are drying agents. What is the use of the drying agents? Drying agents remove H2O vapor. That means moisture. So they remove entire moisture from the this beaker, and imagine this is the reaction. This is the mercury level. Imagine. So the mercury level is like this. Both are equilibrium in stage. Afterwards, carefully removing this calcium chloride and phosphorus pentoxide from the reaction vessel. Then you try to place water or any other liquid. In this case, I am taking the water. After certain time, you can observe that there is rise in the level of the mercury. Level of the mercury rises up and slowly it will stop after reaching certain level. How could this is happening? It happens because whatever the water we have taken inside of this beaker, it slowly starts vaporizing so that it creates the vapor, and the vapor molecules occupy the entire space available for it. Because some of the water is converted into the vapor, the volume of the water also little decreases, and since vapor is created, the pressure inside of the beaker gradually increases. So that pressure automatically pushes the mercury. That's why the mercury level rises up. Then it has to keep on rising because the vapor continuously to takes place. But why this is stopped after reaching certain stage? Because once vapor molecules occupy the entire places, vapor molecules have the gaseous nature. According to the kinetic molecular theory of the gases, gas molecules move randomly in all the directions with high velocities and they collide with each other. So, or else with walls of the container also. So, these molecules may collide with each other or also walls of the container. At the same time, they may collide with the surface of the liquid. That creates the vapor pressure. So, these molecules exert the pressure on its own liquid surface. That pressure is called the vapor pressure. The process of conversion of liquid into the vapor is called the vaporization. After starting, vapor pressure will be more. That's why the level of the mercury gradually increases. After certain time, when the molecules collide with each other, and the condensation also starts. That means the gas molecules start converting into the liquid molecules. So that process is called the condensation. So here we can observe the two opposing process takes place continuously. One is vaporization, second one is condensation. Both process continuously to takes place. So the stage at which rate of vaporization is equals rate of condensation, then there is no change in the number of vapor molecules in the beaker. So once number of vapor molecules no change, then automatically pressure also will not change. Once the pressure do not change, then there shall be no rising up of the mercury level. That means, so this constant mercury level is obtained only when rate of vaporization is equals to rate of condensation. So can we say that for all the liquid molecules, at the same stage, the rate of evaporation condensation can be achieved? No, it depends on the type of the liquid you take here. For example, if you take the more volatile liquid, they can create the more amount of the vapor, so that the mercury level rise up more. So here, for example, if you take ethyl alcohol, second one is diethyl ether in separate beakers. See, ether is more vaporized, more volatile than the alcohol. That means ether can create the more amount of the vapor, so that reaching the equilibrium is less for the ether in comparison to the alcohol. So here rising up of the mercury level will be more in the case of the ether in comparison to the alcohol molecule. Alcohol is more volatile in comparison to the water molecule. So that's why different molecules achieve equilibrium at different stages. And third one is solid gas equilibrium. So how to observe the solid gas? Conversion of the solid directly into the gases is called the sublimation. That means this concept is applicable only to the sublimable compounds. Example, if you take the iodine, solid, can convert into the iodine in gas state. Iodine in gas state has the violet color. Similarly, camphor, solid state, can be converted into the camphor in gas state directly. There is no liquid phase. Similarly, ammonium chloride, solid state, converts into the ammonium chloride in gaseous state. That means it completely sublimes. Then how to observe in this type of the cases the processes attained the equilibrium or not? Very simple, that you take a beaker, a transparent beaker, try to keep the iodine in solid state which has no characteristic color, but after certain time vaporization occurs, that means automatic sublimation occurs. Slowly iodine vapor molecules are observed because they have the violet color, so that we can understand that the intensity of the color gradually increases. But after certain time there shall be no change in the color of the iodine vapors, so we can understand at that stage the iodine vapor molecules conversion from the solid state becomes equals to the conversion of the iodine gas molecules into the solid state. That means both achieved the equilibrium process. Dear students, I hope you understand the introduction part of the equilibrium. We shall meet in the next class. Thank you one and all.